Welcome to Spring LIB.
So in the cyclotron, for example 32-2, we are using uh, different particles. We are not using alpha particle. So in this case, we are asking ourselves what would we get if we were to change the particle to an alpha particle. So we know that the kinetic energy, this equation is given as q square b square r square over 2m. Now compared to the example, right, the charge for this case, the q is double, right? For an alpha particle is 2 plus 2. So in this case, the kinetic energy must have been quadrupled, right? Because it is squared, right? Other than the charge itself, the mass is also changed. The mass is also quadrupled because there is 4 nucleons for our alpha particle, and so the effects will cancel out. The magnetic field and the radii are kept constant, right? So they are unchanged, and so the kinetic energy should be unchanged and would be 8.7 MeV, right? Which is given in the example. Try to calculate that out. Now to find the velocity, we equate kinetic energy to be half mv squared, right? Assuming that it is not that relativistic. So half mv squared, we can find v to be 2ke over m. Let me take the square root. Now the kinetic energy, since it is in terms of MeV, we'll have to convert that into joules to get our velocity. So we multiply by the conversion factor over here. That's 1.6 times 10 to the power minus 13 joules per MeV. And we divide by the mass of our alpha particle, that is because it has 4 nucleons, so we just take 4 times of the mass of a proton. It's very close to the mass of a neutron as well, so not much difference. Our answer should be 2.0 times 10 to the power 7 meters per second, which is less than 1%. Alright, less than 10%, sorry, of our speed of light. So it is a valid assumption. We can just use the non-relativistic version. Now, considering the deuterium case, now for the case of deuterium, same thing, we're going to use the same kinetic energy equation. But in this case, you see that for deuterium, the charge isn't changed, right? It's still plus 1e. So there's no change in the charge, but the mass has been increased by 2, right? It has been multiplied by 2 because for deuterium, it contains 2 nucleons. So in this case, we expect that the kinetic energy will be halved of what we saw in the example, which is 8.654 MeV, and so we should get about 4.3 MeV because the mass has been halved. Now we can find the velocity by taking half mv squared is equals to 4.3 MeV. We do the same process of conversion from MeV to joules. Right, not forgetting the square root. the mass in this case is 2 times of the mass of a neutron or proton, and the speed we get would be 2.0 times 10 to the power of 7 meters per second, which is the same speed as our alpha particle. Right, and the reason behind that is that they have the same charge to mass ratio, and so they must move at the same speed, right? Now the frequency of the voltage, to find that, we use the equation QB over 2 pi m. Now remember, we said that they have the same charge to mass ratio, right? Because for alpha particle it is 2q, 2e. The mass is 4 times the mass of a proton, right? So that is equals to E over 2mp, right? Which is for our deuterium. Right? So they have the same ratio. They should have the same frequency, right? Because in this case we are just taking constants, right? B over 2 pi times the charge to mass ratio. So we can just use either case to find the frequency. So maybe we use the deuterium one, since it is simpler. So we just need to substitute the values in. For the equation, but remember that for the example 32-2, the example is for a proton where the charge over mass ratio is given as E over mp, and the frequency that we get is 25.94 megahertz. So in this case we are just adding a factor of 2 inside, so we just have to divide our frequency by 2. We should get 13 megahertz. So this would be our frequency.